let's start. Do you have any questions? Okay, so we were discussing, I think, 4.3.1, sorry, 3.4.1, conditional variance formula, or yeah, computing variance by conditioning, right? It's the same thing. Which says, right, that variance of x is expectation of conditional variance plus variance of conditional expectation. All right, and we proved the formula last time, so we're not going to repeat that again. In terms of use, right, obviously this is used to compute variance of a random variable. And the challenge is very much the same as the challenge of computing expectation by conditioning. That is, right, you have to find the appropriate random variable to condition on, but also, right, that you have to compute these terms. And these terms for variance would be, let's say, harder to compute, or you will be more likely to make mistakes if you're not careful, okay, in terms of in terms of the conditional distribution. So again, when we take, let's say, the inner operation, right? The inner operation will affect the x, while the outer operation will affect the y. That's always the case. But if you kind of mistake the sequence, then you get the wrong calculation. And so, well, we're going to just go through several examples, right, to demonstrate how this formula is used. But the rest of them, right, it's just really about, practice. You go through the problems and you kind of really try to see, right, what's going on. And I guess the last remark is, if you found the right or the appropriate random variable to condition on to compute expectation, right? If you have an appropriate y to use in this formula, then it should be the same y, right, that is used in the variance calculation. So the choice for the old problems, right, the problems we did before, or the problems assigned in the homework, the choice, if you move from calculation expectation to variance, would be the same choice. It's just that the computation will be harder, okay? But if you move to a new problem that we haven't seen before, then, basically I'm just trying to say that when you calculate, right, expectation and variance, it should be the same random variable that you condition on. That would be the appropriate one. So you don't have to make your guesses twice, right? If it works, it works, but the computation will just be harder for variance. I guess let's start with, right, the familiar geometric random variable. Okay, we know, right, that expectation is 1 over p, right? And we did it by conditioning. What did we condition on? Well, we condition on y, right, as the result of the first trial. Okay. Now let's see if you can apply this formula and calculate variance of x and see what that is by conditioning on the same random variable. Okay. When you apply the formula, what do you get? And is there any difficulty, right, applying the formula itself? So everything, right, start with the conditional distribution analysis. So x given y equals to 0, oh, okay, x given y equals to 1, right? If the first trial is a success, then you only need, right, 1 trial to find the first success. But if the first trial is an error, is a failure, then you need, right, to repeat the experiment again to find the first success, right? Wasting 1 trial. Okay, so let's see if you understand this. Then what is conditional variance of x given y? Can we understand what that is in this case? Well, here, right, if you remember, the operation is going to work on the x, right? But there are 2 scenarios, whether y equals to 1 or y equals to 0. So here we should also separate out the scenarios. So in other words, right, it's going to be clearer now because we have to be a little more careful with our analysis. But conditional expectation and conditional variance, they are random variables, okay? Meaning that they will take values with some kind of probabilities. In this case, right, what kind of probability? The probability of y being 0 and 1. Okay, so it's very natural to separate out the cases and then assign the probability for these cases what you're conditioning on, as long as you have a discrete random variable. I mean, it doesn't have to be like the only way to proceed, but here, right, that will be the way. So for example, right, when y equals to 1, then this is a conditional distribution. Then what is the conditional variance? And the answer is 0, right? Because 1 have variance 0. Then right? It should not be surprising that the conditional variance here, y equals 0 is just variance of x. Because variance of 1 plus x tilde is variance of x. X tilde has the same distribution as x. All right. And so, of course, right, this will be one minus p times variance of x. Any questions so far? And this is what I mean by the complexity, right, of the calculation when it comes to conditional variance formula. It'll just be harder, and you have to be more careful. You have to really understand what conditioning is about to execute the computation. Okay. Well, what's next then? This one, right? So expectation of x given y, again, will be natural, right, to divide into cases. And we'll see that, right, this will be 1 with probability p, 1 plus expectation of x with probability 1 minus p. Well, we do know what expectation of x here is, right? After all, we have worked that out. So we can write that down as 1 over p. Okay. Then what are we doing? We calculate this. So variance of conditional expectation will be what? So variance of this random variable, right? Well, what do? You have nothing better to do than just to apply the formula, which is expectation of the squared, really 1 square, right? Minus the square of the expectation. Okay. Any question? So, well, if you put everything together, right? And it's probably best if we clean this up because we want to write down, right, what the final answer is. And the final answer for geometric is a nice one, right? What is it supposed to be? The answer is supposed to be 1 minus p of p squared, right? How do we know this? Well, we just look it up online, right? So this is the supposed answer. So we, want to, right, be able to verify that. So let's work this guy out a little bit more. Well, what is it, right? Is, let's see here. P plus, right? So that's 1 plus 2 for p plus 1 over p squared. Times 1 minus p. And then minus, right? Well, what do we have here? So that's 1 minus 1, which is 0, right? And then plus 1 over p minus p. But p minus p, right, cancel. So we only end up with 1 over p squared. Okay. And what do we have here, right? So that's 1 minus p, right? So that's just 1, okay? And then you got, let's see here, 2 over p plus 1 over p squared, right? That's canceled with this. So we just get 2 over p, right? And 2 over p minus 1 over p, right, is 1 over p. So we got 1 plus 1 over p, right? Am I missing anything else? 1 over p squared is taken care of, minus 1 over p. Hold on. I think I'm missing a minus 2 here, right? So 1 is there, right? The minus p got canceled. And then minus 2, right? 1 minus 2 should be minus 1. So okay. So that's what this whole thing simplifies down to. Any question? All right. So it's this plus this, right? So therefore, variance of x is supposed to be 1 minus p variance of x plus, right, this thing, which is this. So, right, clearly p variance of x will be 1 minus p over p. So therefore, variance of x is 1 minus p over p squared. As, kind of expected, right? So that's what it is. Any question about this? All right, let's do one more. And this time it will be the compound random variable. So remember, right, we have x as a sum of xi, I goes from 1 to n, where xi are iid with mean mu and variance sigma squared. Okay. N itself has some expectation invariance, but we're probably not gonna, give it some extra name just not to really add more symbols. But the thing we want to note is that n, right, is a random variable that takes on non-negative integers, right? So n has value in 0, 1, 2, etc., right? I'm not sure what the notation is. I think it's the natural numbers doesn't include 0, so you have to kind of throw that in if you use a notation natural number, right? Whatever. The point being is, right, this just kind of represent the upper limit of the sum. So anything that's legal, right, for upper limit of the sum can be, right, a value of n. But n also, right, must be or should be whatever independent of the x's, right? So in other words, this is a random sum, not only in the sense of the terms being random, but how many terms you use, right, is also random. And we talked about how to compute, right, the expectation, the natural object to condition on is the upper sum itself, right? Big N. And the moment you condition on the upper sum, upper limit of the sum, then, the condition expectation at least will just operate, like linearity. In other words, we have a sum like this. Okay. And then, right, we'd realize that, well, they're independent, so we can drop the conditional expectation. Now, all this being mu, and finally, right, mu being a constant. So there you go. That's the expectation, right? This is a repeat of calculate the calculation last time, but it's good to just see again. Now, so that's not really a quiz, right? The quiz is about the variance, right? So what is the variance? Can you use conditional variance formula to calculate the variance here? So what do we have? So again, right, we have two terms, expectation of conditional variance plus variance of conditional expectation. Okay. Oh, but what is y, right? Y is clearly n, right? The upper limit of the sum, and x is the sum itself, right? So let's write that down. Like that, okay? And again, right, the whole point is once you fix the upper limit of the sum, then the inner term just appears like regular conditional variance or regular, right, conditional expectation, meaning that you can pass them inside for expectation. For variance, as long as they're independent or they're conditionally independent, and you can pass them in, right? You can pass a variance in. And again, right, they're truly really just all independent. So we can do that, right? So it's expectation of the sum. And notice that it's bad practice to just drop conditioning out of nowhere. So you can just, the point being is you just keep the conditional, right, formulation until the last moment that you have to drop them, then you drop. Okay, but like that. So here we did not do anything fancy beyond, right, passing the operation inside the sum. Once we fix the upper limit of the sum, and we can do that by, well, expectation, you can always do so. With variance, you need independence or you need conditional independence in this case, which you have, right, by the hypothesis. Any question? All right. And so, what do we have? Well, so the next step is clearly just to drop, right, the conditioning because n is independent, right, of the xi. and replace this, right, with their known value. Like that, okay? But, right, the last step, if you're not careful, you will still make a mistake. So the first thing is, right, sigma square expectation of n, but the second one will be mu squared times variance of n, okay? And the most common mistake people do when they calculate, let's say, variance of a compound random variable, is they just take the variance of the individual term, multiply with the expectation of the upper sum. That's only one part of it. The other part is here, right? And again, that's because of the conditional variance formula. All right, any question? Okay. So let's try to apply this to something. This is question number 44, which says what? The number of customers entering a store on a given day is Poisson 10. The amount of money spent by a customer is uniform 0 to 100. Find the mean and variance of the amount of money that a store takes in on any given day. Okay. So we should recognize what? Should recognize that the amount that the store receives, right, would be clearly, right, the sum over the amount of money spent by all customers during the day, which will be, right, if you let X be the amount received, right, called total received, right, in a day. And of course, xi being the amount spent, right, by customer I. And of course, n being the, right, total number of customers coming into the store, right, in a day. Then this line up like so, which just means, right, that the random variable in question is a compound random variable. Okay, and I think we talked about this last time, right, when we introduced a compound random variable. This doesn't have to be the only way, but it's one of the, let's say, popular way, right, that compound random variable will show up when you have a Poisson, right, arrival describing certain kind of events. Then and then each of the event, right, takes on certain kind of random value. They're all the same, they're all IID. Then the total, right, amount of that event across all arrivals will be a compound random variable. Okay. Sorry, give me a moment. And so once we realize, right, that it's a compound random variable, then all we have to do is just to apply, right, the formulas. That's it. And so therefore, right, well, you can repeat the calculation. It will be useful, right, for you to repeat the calculation to remember where the formula comes from. But in the end, right, it's just going to be what? This is going to be mu expectation of n, where mu being the average value of the xi, right, which is uniform 0 to 100. So, right, which is uniform 0 to 100, right? So that's going to be 50, or, let's even, it's 100 over 2, right? The expectation of a uniform multiplied with lambda, which is 50, right? Sorry, 10. So that's whatever that is. And the variance will be, right, sigma squared times expectation plus mu squared times the variance. Well, sigma squared being the variance of the xi will be 100 squared over 12, right? And then, of course, times lambda. Mu squared, though, is a second move. Sorry. Yeah, mu squared, right, being just, well, whatever that is here, right? And then times variance of n, which is also lambda. And again, whatever that is. Any question about this? All right. Let's continue with the next question. And this will be number 46. So question A, show that covariance, right? Covariance of two random variables is the covariance of x and then expectation of y given x.
Excuse me, Professor, can you just scroll up for a second? Okay, thank you.
Mhm. All right, so first let me point out why this formula might be relevant. It's not just a weird theoretical question. A lot of times, conditional expectation of y given x will be a nice thing to look at, for example, in linear regression. Okay. You may or may not realize it, but in linear regression, what you look at, right, is something like y given x is ax plus b plus some error, right? So in linear regression, it's not y is equal to that. It's y condition on x. I mean, several ways to look at it, but do remember, right, that the covariates are the ones that you regress on, right, are constants, however you want to look at it. So one way is to condition, right, on the covariate. And of course, there's an error term, right, which is usually normal, zero sigma square, whatever. So this is the assumption, which is saying, right, that the conditional distribution of y given x is the linear function of x plus some error. Of course, the error term here makes the conditional distribution not an easy object to look at. But if you take expectation, then clearly, right, notice you already fix x. So x here is a constant. So when you take expectation, nothing happens. The expectation here will operate on the error. And the error is normal zero sigma squared, so it's just zero. So expectation of y given x is this. And so you see the relevance here is that, right? Of course, a lot of times you want to find the covariance between, the I think this is called the dependent variable, right? Whatever, and this is the explanatory variable. That's another name, right? Whatever. So you want to find the covariance between the two guys. Now again, right? The covariance between these two guys might have complex. Let's not say complex, but whatever disjoint distribution, whatever joint distribution. But if the conditional distribution is like this, and the conditional expectation is like that, then by this formula, you have this, which will just give you a variance of x squared, because covariance of x and b will be zero. Okay, and so that's just one particular example where this formula might be useful. Okay, but it's not just. I'm just trying to show you that this is not just a empty, theoretical consideration. How do we do this? Well, you know, we will start working from, I guess, the more complex part, right, to the simpler part. So the covariance of this will be, right, expectation of the product, right, minus the product of the expectation. Now, notice that, right, x is being a constant here because x is fixed. Therefore, you can move the x inside here. X being a constant with respect to conditional expectation. So you can move it inside. And then notice this is just a double expectation. So that's just an expectation. But this, yet again, is a double expectation. So it's just which of course, right, we recognize as covariance. Any question? So I guess part B, right, is just what I told you about. So they just switch A and B, I guess, but suppose that conditional expectation of y given x is a linear, right, function of x. I guess I was doing ax plus b. Here they do a plus bx. Doesn't matter, right? They ask you to show that b is covariance of x, y divided by covariance of x. So probably this is just a different way, right? Oh, sorry. Sorry, right? Covariance of x and x is variance of x. It should not be variance of x squared. So I wrote it wrong here, right? It's covariance of x and x is just variance of x. So clearly, right, it's just exactly what I just wrote here, right, with a being replaced by b. But the meaning is probably slightly different. Here, I was advertising, let's say, right, for finding covariance in terms of this. But I guess I forgot, right, that in the context of linear regression, let's say, the goal is to estimate, right, the coefficients. Okay. So here they told you that if you have linear regression going on, then the slope, right? So the slope term will be the covariance, right, of y and x divided by the variance of the explanatory variable. So there, that's how you estimate the slope, right? And if you look into the formula, the textbook formula for b hat, right, for linear regression, you'll see that it's going to be the empirical covariance divided by the sample variance, right? Empirical variance of x of the data. So like that, right? So I already did it, right, on the previous part, so there's nothing to do here. Just pointing out that that's really, right, how it's used. Any question? All right. Well, let's do one more on variance, and then we'll move on to the next material. So this is quiz 6, I think, right? So quiz 5. If condition expectation is 1, show that variance of the product is at least variance of x. Okay. How do we do this? Well, clearly, right, with this going on, then, and with the theme of, right, the section, then the key is, conditional variance formula, right? And we condition on x. Like so, right? And again, remember, right, if you condition, then whatever you're conditioning on is viewed as a constant within that context. So therefore, right, the first expression, x can come out as x squared. Right, so we have that. And then what do we know? We know that this guy is 1, right? So therefore, I guess we don't even have to work on the first term, but like that, right? So the only thing to recognize now is that, well, whatever this is a non-negative, right, random variable, because x squared is non-negative, and variance, however you calculate variance, will be non-negative. So therefore, the whole term is non-negative. Well, that's all we need, because that's, right, what we can use to conclude that this is variance, bigger than variance of x. Any question? Right. So let's move to the last topic we want to discuss for this chapter, which is 3.5. Computing probabilities by conditioning. And the first thing to note about this is I don't even know why it's a separate section. I mean, I'm just following the textbook, so I call it a section. It really there's nothing new here. This really can be encapsulated within condition expectation. Okay, but maybe that's the only thing to point out. That basically, so here's the thing, right? First of all, I guess the only thing to note is that when you have an event, all right, let's call it the event F, just not to confuse with E being used as expectation. So if you have an event F, then probability of that event is the same as expectation of the indicator function that event happens. Okay. So we mentioned this before when we discussed the Bernoulli random variable. Right? The reason is the indicator function is a Bernoulli random variable. So if you remember, right, a Bernoulli random variable has expectation P, right? And so clearly this is Bernoulli with P being the probability that F happens. Therefore, probability of F is expectation, right? It's just, well, so first of all, it's a very simple recognition that this is the case. On the other hand, it's super useful in many contexts. I mean, first of all, right, as far as we're concerned, then whatever statement we can make about expectation, we can make about probability. Like what? Like so, right? That's why I say, right? So for example, if you want to calculate probability, right, of something, well, what this says, well, go ahead and consider it as an expectation. But the moment you consider it as an expectation, then you can apply a conditional formula on it. Whatever you want to condition on, right? A lot of times, probably this guy is another indicator function itself. So indication of Z, whatever, right? But it doesn't have to. It can be, right? The moment you call this a random variable, you can condition on any other random variable. But a lot of times, right, this can be called conditional probability of the event F given the random variable Y. Whatever, right? Things like that. So I will drop this, right? Just not to confuse people. The point being is there's nothing new here, right? It's just really recognizing that probability is an expectation. Any questions so far? Okay. Well, let's do a routine routine demonstration, right? So this one is used a lot. Let's suppose that X and Y are independent random variables, but this one has density. Okay. So we have two random variables independent, but with densities. The context usually, right, is something like IID, but here we allow for them to be different, right? Different densities, but the context, the most common context is the IID. And you want to calculate, let's say, probability that one random variable is less than the other. Okay. Now, let me tell you, right? The usual approach is the Calc 3 approach, right? The joint density approach that you would have learned in 477, right? That says that you want to integrate over the region for x is less than y of the joint density dx dy, right? Well, I guess here let's call du d. Nah, it's fine, right? And the joint density here will be computed by the product, right, of the densities because they're independent. Okay, maybe let's try that step now. And this step, and then this double integral is calculable. I don't think there's not anything that hard about it. But right, then the conditioning approach somehow, right, will be much more natural to me at this stage, and that's the approach that's going to be advertised in this example, because right, it goes along with the theme of the calculation, and so on and so forth. Who knows? But and you will see that actually the answer may be nicer. Who knows? It's the same, really, right? But here, I want to emphasize that I don't think there's any advantage between this approach and conditioning. It's just different flavors. But if you do conditioning approach, right, you will do something like this. You start with this question, and then, right, you try to look around for something to condition on. So it's an event, right? Whatever event that is. Well, what do you condition on? Well, right, clearly y would be a nice thing to condition on here. Because right here, y is random, so that's the hard thing, right? Notice, for example, probability of x less than some particular value, right, would be the CDF of x evaluated at that value. Or if you want to be more particular, is the integral up to that value, right? So the difference right here is that y is a constant, but here y is a random variable. But we can fix that easily, right, by condition on y. And then, of course, right, take expectation. Okay. But here, right, the whole thing plays out as, well, remember, the inside is on the x and the outside is on the y. So therefore, the inside will be probability, right, of x less than, let's say, a particular value of y, because now we know what that is. And then the outside is on the y. So the outside will be with respect to the density of y itself. You know what? Hold on. I skipped one step. Sorry. The inside, right, is with respect to y. So with respect to x for any particular value of y. And the outside will be with respect to y. Like that. And naturally, well, when I do conditional approach, I just move straight to here. I somehow skip that step even, but this step explains why this form is true, right? And now, right, the step that I skipped yet again was to drop conditioning. So again, right, a lot of people just write this, which is true in this case, but it's dangerous. Notice everything we wrote down so far is universally true. We did not even make any assumption about the joint behavior of X and Y. The only thing we need is that Y has a density because we use its PDF, right? But nothing else is assumed, including how X and Y jointly behave. The next step will use the assumption that X and Y are independent to drop conditioning. Okay. So like I said, you could move. I've seen some people move from here to there, skipping, this is just an explanatory step. So it's not dangerous once you get used to things. But this step is dangerous because you did use the independence assumption. And again, it's correct here. There's nothing wrong. But if you're into that habit, you might get a wrong answer, a wrong formula if X and Y are no longer independent. Okay? So like I said, this part is universally true. So if X and Y are not independent, this is still true. You just have to figure out what this is. But if X and Y are not independent, then this is false. Okay? But here we have a nicer thing here. And then of course, this is just the density, right, of X. Sorry, not the density, the CDF of X. Like so. Any question? Okay. So, okay. All right. But this is just a demonstration, right, of something called a conditioning approach to calculate something involving X and Y, all right? So again, the point is that what you learn in 477, the standard curriculum, would tend toward the joint density calculation. Well, as far as I know, most people, when they're used to things, tend to favor the conditioning approach, but whichever one is fine. The next one, though, right, is going to be a relevant example for us. So let's make that into a quiz 6. Because this is one of those going to be like the well-known examples that we should know or memorize. It's like this. And it's kind of very important, so we're going to give it a name, right? The yoga studio problem. Okay. So it runs as follows. So the number of people visiting a yoga studio each day is Poisson lambda. Suppose, right, each person is independently a male with probability P and female with probability 1 minus P. Find the probability that exactly N women and M men That doesn't matter. Males and N females visit the yoga studio on a single day. So what should this remind you of? Remember, right, at one point we did a question probably in chapter 2, right, about number of accidents a day, right, is Poisson. And they say something like an accident is major, right, with probability P, and minor, right, or not major with probability 1 minus P, right? And they ask you for the probability of no major accident, right, on a day or something like that. So this is that problem again, but in more complete details. How so, right? So if you let X, right, be the number of males, Y be number of female, right? Let me say, right, number of, I'm not talking about the gender here, right? The number of male and number of females visiting the yoga studio, right, on a single day, then we do know that X plus Y will be horizontal lambda, right? The sum. What we're being asked is exactly the joint distribution of X and Y. Okay. So that's the importance of this question. So the language there is really just about, okay, right? I have a Poisson arrival where I know, right, that they separate out into types, right? One type with probability P, another type with probability 1 minus P. How do these random variables, right? How do the random variables represent the arrivals according to types jointly behave? So how do we approach this here? So you see, right, that clearly this requires us to condition on something. What do we condition on? We condition on the sum, correct? Well, and then take expectation of that. Okay. So now it's so similar, right, to here. When you condition on something, then you just have to break down that something into the cases, right? Case here for a continuous random variable, sorry, represent, right, a value it can take, multiply with the density, right, the likelihood that it takes on those values. So here we condition on the sum. So what values can the sum take here in this case? Answer? Only one value, which is m plus n, right? Because if x is m, y is n, well, what values can x and x plus y take? So really, right, it's just m plus n, right? So it's really about probability x equals to m, y equals to n, condition on x plus y equals to m plus n times. When you look at it this way, it's actually even simpler, right, than that. This is really the conditional probability formula that we looked at, right, in chapter 1. But of course, right, it's still under the bigger framework of conditional expectation. But right here, it's just really conditional probability. Okay. And then, well, right, we know what this is. This is Poisson lambda, right? So that's Poisson lambda taking value m plus n. So this e to minus lambda, lambda to the m plus n over m plus n factorial. What was this? So the first thing to note, right, is that if you condition on x plus y, then you don't need to have both values. You can just have one value. Seems like I don't have enough space. You understand? The reason, of course, right, because if x plus y equals to m plus n and x equals to m, then automatically y equals to n. So we only need one value, right? And the reason, right? I mean, you can have both, doesn't matter. Because what each person is independently a male with probability P, right? And we're giving the sum. So what can you think of, right? You can think of each person as a trial with success being a male. Well, no pun intended here, right? It's just P in that context. You can switch to female if you like it better that way. But basically, right, it's a trial where the success, right, case is P. And so here we really just look at M plus N independent trials, and we asked for M successes. And so that's a binomial, right? It's a binomial random variable. Like that. Okay. And then the rest, right, the same. Any question? But the story doesn't stop here, right? The story continues. Because M plus N, choose M, is M plus N factorial, N factorial, N factorial. And that will cancel nicely with this. So the first thing we have is 1 over M factorial. And then, of course, right, the P and the lambda goes together to give you something like lambda times P to the M. Similarly, you have 1 over N factorial, right, from the remaining term here. You have lambda 1 minus P to the N. All right. What about the e to minus lambda term? Well, lambda is lambda times 1, and 1 is P plus 1 minus P. So you can split this into lambda P and lambda 1 minus P. In other words, you can have e to minus lambda P here, and you can have e to minus lambda 1 minus P here. And you see, right, that this is it, because we recognize that this is a probability of a Poisson, right? Lambda P equals to M. And the other one is a probability of a Poisson, lambda 1 minus P equals to N. Okay. Now, I guess the question didn't really ask for it, but the real conclusion here is not just this number, or, you know, for that matter, not just this number. The real conclusion, right, or the real question here is about the joint distribution between X and Y, between the number of males and females visiting this yoga studio. And the answer, right, is that jointly they are independent, right? So that's the conclusion. The number of males and females will be independent. Notice, right, that's not at least implied explicitly in the hypothesis, right? You just know that the gender can be independently be male or female. That doesn't for each person, but that somehow translates to the number visiting are independently, each other. Right? Again, it's a subtle thing, and don't take it for granted, right? Because probably you think, well, it depends here should translate it depends there. Maybe not. The Poisson has a lot to do with that. Because, for example, right, I mean, you don't have to have people arriving at yoga studio according to Poisson. They could arrive according to a binomial. They could arrive according to a geometric. I don't know, right? But I think if you change that, then the numbers will no longer be independent. So it's not really just like, oh, obviously they must be the case, okay? But here they are. The number of males and females are independent. Poissons, right? And the rate will be the original arrival rate, the total arrival rate, times, let's say, the proportion, right, of the type accordingly. Any questions so far? All right, so let me tell you, right, the generalization of this. Or the generalized, it's just general result. You can take anything, right? You don't have to take a yoga studio. It's just a context. If X is a Poisson lambda, right? Or I don't know, N. Okay. And let's say, so that's a total number of arrivals. And let's say N can be broken down into sum of, let's say, N sub I or X sub I. But notice, right, this is I from 1 to R. There are types. Okay. The number of arrivals can be broken down into R types. So the above, right, R equals to 2. But these R types, so each arrival, right, can be independently of a type, right? Type I with probability Pi, right? For I from 1 to R, with the sum of Pi being 1, right? So instead of gender, you can do, I don't know, people with jobs, right? People coming to yoga studio with, I don't know, 5 types of jobs. Make that up. Each type of job with certain kind of probability, right? That's what we have here. Then the result will be that the number of arrivals itself, right? So xi then being the number of arrivals of type I, right? Total number, if you will, right? Of type I. Then the result will be that the xi will be independent, right? Mutually independent Poissons with rate lambda times pi. Was a proof exactly as above. Just work it out for R sum. So it will be some sort of like multinomial calculation, but very similar to the above. Any question? Okay. So let's do two more question. Let's see here. Sorry, I'm looking for the question that you were assigned. I can only find, yeah, okay. So where are we now? Quiz 7. So these are both coupon problems, right? Coupon problems are fun. So number 59 says what? Each new coupon is independent of the past. Will be type I with probability PI. A total of n coupons is to be collected. So let AI be the event that type I is present in the collection. Okay. And now they say for I not equal to J, compute the probability of the joint AIJ by first conditioning on N, Ni. This is a number of type I coupons in the set. B, condition on Fi, the first time a type I coupon is collected. And C, just do a common sense calculation. Sorry, the union, yeah, is AI plus P of AJ plus P of AIJ. All right, so let's take a minute, right, or so to digest the question and see the point of the question. Okay. So what's the point of the question? Well, depends on how you look at it. The question may not have a point. If your point is to compute, right, PAIAJ as efficient as you can and as simpler as you can, then there's no point to this question, because really C will be the easiest thing. I mean, A and B are not too bad, but it's not really, I would say, the natural way to think of things. I don't know, right? But we'll see, right? That as at least as far as, let's say, our training is concerned, or the way we tend to get trained in probability, C would be probably the most straightforward calculation. Probably because we just don't think of conditioning as often. On the other hand, right, it sort of kind of demonstrates a nice point here. That is, there are more than one way to condition. There are more than one choice to condition on, right? And sort of this goes a little bit against what I was saying before, which is you need to condition on the right object, right? A right random variable to make the calculation, let's say, doable. Here is probably one of the, let's say, rare example where there are two equally viable choice. Right, okay. And then so the point also is for A, B, and C, they clearly must give you the same answer. If somehow your answers in A, B, C are different, that means you got something wrong in between. They're just different ways to calculate the same thing. But sort of they twist your brain a little bit to have to look at things from different angles. Okay? And sort of like just more exercise on conditioning. And of course, it demonstrates, right, that 3.5 calculating probability by conditioning, but whatever, right? Like I said, it's really just expectation. Okay. So let's see. Probably it's easiest to get the easiest thing out of the way first, right? So also notice, right, coupon problem comes in many flavors, as you should have seen by now. One thing to pay attention to is how many coupons are we collecting, because that could drive the problem in a different way. Sometimes, remember, right, there's no fixed number of collection. You just keep collecting until you satisfy a certain criteria, right? Criterion. So that's called stopping time, right? You collect until you have every type. How many coupons do you collect? That's random, right? Random every time. It depends, right, on when you get every type possible. But sometimes the number of coupons collected is fixed, right? Here, there's n coupons. That's it. So now, right, the number of types will be random, right? In the first example, you collect until you have a full collection. So you have every type. So here, I guess they didn't even tell you how many types there are, right? Say R type. But here, the number of types present in the collection will be random. Right? Anyway, so how do we calculate this? So for example, right, at least by the implication here, these, and these should be easier to calculate than these. And at least you should appreciate why, right? But let's start with PAI, right? What's PAI? Well, the probability that type I is present in the collection. That's not easy to handle. The easier one to look at is the probability type I is not present in the collection because what that means is none of the coupon can be of type I, right? So in other words, 1 minus pi raised to the n power, and then 1 minus that. Meaning that we just use a complement here, right? And that's exactly the reason why this guy is easy and that guy is hard, right? Because, let's fill this in. This is both coupons present in the collection. Well, what does that mean, right? At least one coupon must be of type I, and at least one coupon must be of type J. How many, actually, who knows? But if you look at this guy, again, this guy by itself doesn't seem like easy. The probability that either coupon of type I or type J is present in collection. But the point, right, is that its complement is very easy to calculate, right? So, because, right, that's by De Morgan's law, De Morgan's rule, right? This is that, right? That's the only reason why, right? It's easy. Because not type I and type J have present in the collection is easy, because that means none of coupon can be of type I or type J. Sorry, if you just look at that, and that's that. So therefore, right, this is 1 minus that. Okay, so the equation would go like 1 minus pj raised to the n like that. And right, so it means or you subtract over here, it means you got 1 like that. Any question? And so, right, A and B should give you the same answer somehow. So let's focus on A, right? If you condition on Ni the number of type I coupons in a set, how does that work? So probability of AI AJ is, right, let's say expectation of condition Ni. The number of type I coupons in the collection, how does that work? So first thing, right, is to develop the formula. Well, right, because again, we're just going to go through the cases. Ni being what? The type I coupons in the collection. Well, can take any values from 0, right, to n. And here, right, probably you just develop the formula for everything. But notice, right, for example, when k equal to 0, what does that mean? This is just help your conditional thinking, right? When k equals to 0, means no type I coupon is in the collection by definition Ni. Then this will be 0, because then cannot, right? AIAJ cannot happen. Similarly, when n equals to Ni equals to n, that means all, right, coupons of type are of type I. Again, then AIAJ cannot happen. Why? Because there's no room, right, for type J to be in the collection. Okay. So in other words, you can just replace this with 1 to n minus 1. I mean, useful or not, who knows, but at least, right? I mean, it's probably useful because you have to really, right, analyze this in general anyway. But this is just, kind of throwing out, right, some easy cases. What about probably Ni equals to k? Well, each coupon, right, is of type I with probability pi. So this is going to be a binomial, right, random variable. Okay. See, so the only thing left is to work out what this is, and we're done. Now, so when there are k, so what situation are we in? The n coupons total, right? N total, where k of them, are of type I. Okay. And you want to know the probability that INJ are present in the collection. What does that mean? Well, since we throw out 0, right? The type I has already been present. AI is already there. And we throw out the n, right? So AJ is possible. But anyway, right? What it really means is among the n minus k coupons, at least one, right? So the remaining n minus k coupons, at least one must be of type J, right? That's it. That's the value of conditioning. You kind of know more information. And that's why at least Ni is the right thing, right random variable to condition on, right? So we just have to figure out, right, what is the distribution of the present of type J in the remaining n minus k random variables. What would that be? So we'll look at, right, the distribution of the number of type J coupons in the remaining, right, n minus k. I guess this word is important. Coupons. What would that be? So let me give you an answer, right? Is it binomial n minus k pj? The answer is no. Why not? The why not here is a bit subtle, but when we condition on k of the types being type I, and when we use the word remaining means that the n minus k coupons here, none of them can be of type I. Does it make sense? Because, right, we already look at all types I there are, and we look at the remaining ones. So the remaining one thing we know, besides the fact that there are n minus k left, is a fact that none of them can be of type I. What does that mean? That will influence the success probability here. The success probability is no longer Pj, because if that's success probability, then if you sum up all probabilities, then you should get 1. But I is not present among these possibilities. So therefore, it's going to be Pj over 1 minus Pi. Representing, right, the fact that you are weighing the possibilities of the n minus k coupons with respect to I not being present. Okay? In other words, right, this will be the sum k from 1 to n minus 1 of n to minus k choose, sorry. And then what else? We want at least, right, 1. So again, we will look at the complement, right, which is none of the remaining n minus k is of type J, while also not being of type I. So that will be 1 minus 1 minus Pj over 1 minus Pi raised to the n minus k, like that, multiplying with n choose k, Pi to the k, 1 minus Pi to n minus k. Okay, so far? So that's the answer. And somehow, right, if this answer is correct, it must be the same as this answer. So at least let me point out to you that there's some chance that this is true, right? Because if you look at the common denominator here, you'll get, right, 1 minus Pi minus Pj. And 1 minus Pi to n minus k can go in here, right? Okay, like that. And So you see, right? This is n choose k, pi to a k, 1 minus pi to n minus k. Each of these is a binomial sum, right? Sorry, n minus 1. Right? Each of these is a binomial sum, right? But the binomial sum here, right, is missing the 0th case and the nth case, right? So for example, the first sum would be 1, but missing the 0th case and the nth case, right? So the first one will be 1 minus, right? The nth case will be pi to the k, sorry, and the 0th case is 1 minus pi to the n. Let's see, right? And then this will be also binomial sum, but they sum up to 1 minus pj, right? So it will be subtracting, right? I'm not sure if I'm doing it right here, but 1 minus, right? Sorry, 1 minus pi minus, the sum is 1 minus pi. And you subtract the 0th case and the nth case. This is the nth case, and the 0th case is I think also pi to the n, right? Like that. Let's see if we're lucky here. This cancel, right? This cancel. And then you got, the only thing that's concerning is the 1 cancel. So it seems like right now the answer seems to be pi minus 1 minus pi to the n minus 1 minus pi, and then plus pj, right, to the end, which is not what the other one is, right? The other one is 1 minus this minus that plus that. So I'm missing, sorry. So the 0th case here, the 0th case here is 1 minus pj to the n, right? Like that. So in which case we do have 1 minus pj to the n, like that. Hold on. So 1 minus. Anyway, sorry. Maybe let me, it's best not for me not to really try to, right, handle this at this time, right? Anyway, this is the correct answer, right? You can plug in the like a program, right, and check that they agree. Well, I'll look at home, right, and see how they match up using the binomial formula. But obviously, I fumble, right, with this expression because of the edge case. But okay. Anyway, so I mean, at least they have a chance, right, to be equal, and they're actually equal. But it's not important that we develop them to be exactly equal. I'll work it out at home, and I'll post the notes for you. All right, any question? So we have part B left, right? And we also have So we have part B left, and we also have number 63 to go over, and we have 3 more minutes. So you know what? I think let's leave these two for next time. And so here's the program, right? These are the only thing left that I want to discuss in this chapter. And then, so after we're done with these parts, then we're going to move on to chapter 4, okay? Markov chain on Friday. All right. And I'll work this out real quick, and I'll post the notes once I, match up the answers for you. All right. Any question? All right. If not, then I'll see you on Friday.